Alrighty, last review, so exciting. For anybody who is wondering what's going to happen now, I have 3 office hours next week. One is on Sunday at 7:30 p.m. I hope to see some of you there, especially if you have any trouble with what we've been reviewing and what's been in the videos. And please kind of check out the videos. You don't have to watch them per se, but do give them a scan before coming to the office hour, because I don't want to have to refer you back to slides and things. As well, I wanted to say that all of these slides are posted in your extra notes section on your Blackboard page. I think that kind of gets lost with some people because they're asking where the slides are. So please look at the extra notes part of your Blackboard page to find everything about the final exam slide stuff that's being reviewed. All right, so the one thing I wanted to go over really quickly is that, let me just kind of move this up. Let me just exit this and move this up here. Okay. And the one thing I wanted to go about first is saying that there are 2 ways to get Ecell. And I don't mind which way you do it, just pick the one that you like. So in this example here, I can see that I have copper and silver. And copper is the one that is losing electrons, therefore is oxidized, and silver is the one gaining electrons, therefore the one being reduced. Okay, so we knew the reduction of the silver will occur at the cathode, red cat, and so when we look at the half reaction of the cathode, it's going to be plus 0.8. Great. And then I know the oxidation of Cu is occurring at the anode and ox, and therefore the reduction potential of that is going to be plus 0.52. I get these all from a reduction potential table that I do not post on here because it just wastes space. So method 1 is I take the Ecell and it's the cathode, so E cathode, subtract E anode. Okay? So there's no switching of signs, I just plug them in as is. Now, the other way you can do this is E reduction plus E oxidation, but you have to flip the sign of the oxidation. Okay? So E ox actually equals negative E red. And remember, these are both reduction potentials. But E ox means that you need the oxidation potential, and the oxidation potential would be the opposite sign, right? Okay, so then what I would do is I would take what's being reduced plus what's being oxidized, but this, of course, is a reduction potential, and so I flip the sign to give the oxidation potential, and therefore I get the same answer. Again, what I'm trying to get at is that you have to be able to use one method throughout. I would never mix them up. You never have to choose between 2 methods. You only have to know which method you like and which one you're going to use. So never switch between them, or it's a mess, and it will get you the wrong answer as well. And then how do we get the oxidation state? So many people have asked me this, and especially the next few slides, I hope these steps will be a bit more evident. But basically, if something is in an elemental state, so if it's Cu, say we go back, this is 0. This is Cu, it's in its elemental state, it's 0. If the atoms are monatomic and they have an oxidation number, it's equal to their charge. Again, Cu plus, therefore this is plus 1. In compounds, fluorine is assigned a -1 oxidation number. That's because it's in the halogens, and the halogens all have a -1 oxidation number. Oxygen is usually given -2, unless it's a peroxide compound, which you will not be particularly asked to look at, so don't be too alarmed by that one. And then a hydrogen is usually +1, except for when it's a hydride anion, and you will know that when you look at the monatomic. So if you have CuH, well, Cu plus and H would then be minus, because metals cannot be anions, but hydrogen can be either or. And then in all compounds, all other atoms are assigned an oxidation number so that the sum equals the species and the equal charges, blah, 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 blah. So that's meaning that if you have a complex, that whole entire complex, say, equals +1, then everything in there will adhere to that charge. And so the thing that is nice about that is usually the thing that can arrange its charge a bit is transition metals. And so we're going to look at that in the next slide. So when I'm balancing, the things that I wanted to point out for this, basically with balancing equations and redox, is please don't panic. I know sometimes our math doesn't come out correctly and we're like, what do I do? And the things I would check again is your units. Are you in the right units? Checking if you have the right number of electrons, double checking your number of electrons, but not double checking to the point that you again panic. Understanding the flow of electrons, because remember, it's all about electrons here. Okay, how many, who has them, who wants them, etc. And remember, reducing ones are gaining electrons. Oil oxidation is loss and reduction is gain. And then oxidizers are the ones that are losing electrons, and therefore they want to get rid of them. So kind of keeping those things in mind as you move through these to give yourself common sense checks that, this doesn't seem right because I know that oxidation is loss of electrons, the same as I know that reduction is gain of electrons. So when I do oxidation, I like to think of it as a giant algebra problem with more unknowns than I need. And so first I'm going to look at this one. This is a complex, and I notice that it has no charge, and therefore the overall charge is going to be 0. The next thing I'm going to look at is that CO I know is neutral, and I know that PPH3, or triphosphate phosphorus, is also neutral, and that means that my charge on my osmonium is going to be 0. And then I know that because it's 0, it's a D8 transition metal. If you were to say be doing the splitting diagrams, so you know that you have 8 electrons to play around with. All right, this one. All right, this is a complex that has 4 attachments onto it, so it's either square planar or tetrahedral. And I notice that I have 3 different types of ligands here. So the first thing I'm going to note is that my methyl is going to have a charge of -1. This is because I know that methane, CH4, is overall neutral, and if I take off a hydrogen, therefore CH3, I am missing a hydrogen, and therefore it is CH3 minus. I know that PPH3 is neutral. This triphosphate is neutral. Wonderful. And I know that chloride, which is, I was going to say Cl, chloride, which is a halogen, is also going to be -1. And so if I have -1, then I know my iridium is going to have a +2 on it. And since iridium is a D9 transition, or sorry, we say D9, I don't like to say it that way. It's 5D7, 6s2. The 2 electrons come up from the outermost 6s orbital and move down to 5D7. In that case, in the case if you were going to be doing a splitting diagram. All right, for this iron tetrachloride carbonyl with a bromide, this is a salt. And this salt means that I really don't count that bromide as a ligand because it's going to dissolve off. It just means that this entire complex has a -1 charge on it. I know that these Cls are going to have a charge of -1, and I know that this CO is neutral and therefore 0. And so if I have -1 plus 4 on this side, then I know my iron is going to have an overall +3 charge in order to have the whole complex then equal -1, right? Because if this is +3 and this here, these here are -4, and this one here is 0, then for that all to equal -1, this would have to be +3, right? And again, same thing, I take out from the outermost first, and then the inner, and then the d electron that's the second outermost, and I get d5 overall, just in case you wanted to use this example for, say, splitting diagrams. Because the nice thing about these oxidation states is that you also learn them when you were doing the crystal field splitting diagrams. All right. All right, here's what, this is a quick review about doing redox in different conditions. So I'm going to go through neutral, acidic, and basic. If you want more practice with those, I've put a balancing redox PowerPoint slide on your extra notes part of your Blackboard page, and as well onto your YouTube page. So please go check that out. Okay, so I like to put the steps here. It helps me keep everything together. If I'm in neutral conditions, I know that that means there's no hydrogens, hydroxyls, or water that's really going to affect my overall balancing. So I'm going to write the F reactions and balance their charge by adding electrons. So again, I have copper 3+, so I'm going to have to add 3 electrons here to balance that 3+ charge. Same with my zinc. I'm going to have to add these 2 electrons. Someone asked me, how do I know that this is the one that I'm adding the electrons on this side? And that is because not only is the +3 charge on this side of the reaction, but I know overall that the copper here is being oxidized. And that's because it's going from 0 to +3, and therefore got more positive. Same thing with the zinc. I'm going from 2+ to 0, and that means that I must have gained electrons, and therefore that's why these electrons are being added in the reactants. Okay, I need to balance the charge by adding the 2 lines together, and that means I have to get these electrons to cancel. So I'm going to multiply this top row by 2. I do that because what I like to think of is I take the charge, multiply it by the top row, and then I take this charge and I multiply it by the bottom row, right? We can see how that kind of works. That's how I do this when I think of ever balancing something that's in neutral conditions. And so I multiply this row by 3, and I multiply this top row by 2. and then I add them together. And I simply take everything that is on the reactant side and I put it on the reactant side, and then I take everything that is on the product side and I put it on the product side, right? The thing that I want to note is that's because the electrons all cancel. If you had, and you will see in the acidic and basic equations, but if you have other things that could cancel, i.e. hydroxyl groups or water or hydrogen ions, you do need to cancel those out as well. Everything needs to be reduced to its lowest form, and that means if they're on opposing sides of that arrow, they are cancelable. Cancelable, that is a word. All right. Now, in acidic conditions, so the main thing I want to point out with acidic conditions is, first of all, you do need to find the half reactions, and you do have to balance everything besides O and H. But now we have to balance the oxygens by adding water, and this is where a lot of people flip things around and they add hydrogen first. And I don't know how you're adding hydrogen. Some people just add water and don't add the correct number of water because they, I think, get nervous. But I count here 7 oxygens, right? 7 oxygens, and therefore I'm going to add 7 oxygens onto this overall reaction. The carbon actually comes out as a gas, and a lot of people are asking me, like, what? And I'm like, this is carbon monoxide, so overall it comes out as a gas, so this carbon is not included in the overall, how to put this? It's like, it turns into graphite, and I didn't include it in here because it has nothing to do with the balancing of this reaction, because it turns into graphite and therefore it's a solid. But some people were asking me when I sent this as a practice problem to them, so just to clarify for them, when I said it's a solid and doesn't count, what I meant was that it turns into graphite, and that has no redox potential anymore at all, unlike water and hydronium and all those things, so to clarify. Anyway, moving on. So I balanced this way. I added my 7 waters, and therefore I have to add in 14 hydrogens in order to balance out the newfound hydrogens that I've added into my equation, right? We're always trying to make sure that it's equal balance on either side of what we add at this point. I know on this side I have a -2, and this side is 0, and therefore I need to add 2 electrons to balance out this equation. On this side I have +12 because I have +14, 14 times 1, and -2, so 14 minus 2 is 12. Over here I have 3 plus times 2 is +6, and then water is neutral, and therefore 7 times 0 is 0. In order to get these to balance, I then need to add 6 electrons to this side, because if I subtract 6, then it'll be +6 on either side, so I add my 6 electrons here. Then I need to make the number of electrons equal and add the half reactions, and to do that, just like I said before, we have to make sure that this number of electrons equals this number of electrons, and 6 and 2, the lowest common denominator is, lowest common multiple is 6, and therefore I would multiply this whole thing by 3, right? So then I have to make sure that all of my coefficients also get multiplied by 3. Please be sure you do that. And then I get +6. Awesome. Now I'm just going to add them together. Again, anything that cancels out. I didn't add any water to this first reaction. Sometimes you do add water to the first reaction, so be aware, because if you did, these hydrogens would cross out and the waters would cross out because there'd be them on this side of the equation. All right, so I simplify everything down. I take everything on the reactant side and I put it on the reactant side. I take everything on the product side and I put it on the product side. And then I go through and I just do a quick check to make sure everything balances to +6 and equal charges on either side. It doesn't have to necessarily be +6. But right, I have -1 times 6 is -6. I have 14 times +1 is +14, and I have -2 still. I have still +6, and then I have 0 from water and 0 from difluoride. And therefore, +14 minus 8 is +6, and +6 plus 0 plus 0 is 6. So we've done it. All right, basic conditions. Basic conditions are fun. So basically, I'm going to write 2 half reactions here. This should look a bit familiar. I'm going to balance everything that's not oxygen and hydrogen. Luckily, they do all balance. Then I'm going to balance the oxygens by adding water. Here, I have this oxygen attached to this hydrogen, and I know that I'm going to balance the hydroxyls separately, so I'm just going to move straight down to this next step for this one and not add a bunch of waters that then will cancel out and give myself extra headaches. But because this one has freestanding oxygens and no other complications, I'm going to add water as is. And I know that if I add 4 waters, I need to add 8 hydrogens. But we know that because we're in basic conditions, I can't really have freestanding hydrogens because they are going to get eaten up by hydroxyls. So I have to add 8 hydroxyls. And remember that you can't just add things willy-nilly. It has to equal on either side. So I have to add 8 hydroxyls to the other side, because It's like the idea of adding an intermediate. If you add something to the product or the reactant side, it gets eaten up and then produced on the other side, and therefore it's technically like canceling out. Because remember, like I said before, we want our 6 electrons in that previous one to have 6 electrons on the reactant side and 6 electrons on the product side, because then they cancel out. So this is kind of like multiplying it by 1 in a sense, but in chemical terms. So then I bring this down here, and everything has become balanced. Wonderful. The only thing that I want to know is that, remember, if you have hydrogen ions and hydroxyl ions, they will form together to make water, right? That makes sense. Okay, make the number of electrons equal and then add the half reactions. So basically, I see that I have 4 times -1, and this is 0, and then I have -1 as a whole complex, so I'm going to have to add 3 electrons to this side. Over here, I know that this is 0. I know that this complex is -1. Again, I have -1 here. It's kind of hidden. And then I have -1 times 8. And so overall, this is -9. In order to make this more negative, I'm going to have to add 8 electrons, because that's like adding 8 -1s plus this -1 to give me -9. All right, and then I need these to equal each other. So I have 8 and 3. They do not have a least common their least common multiple is 24, and so I'm going to multiply this one by 3, which is a doozy, and multiply this one by 8. And then when I do that, I find that I get 24 electrons. Wonderful. And then I look through here and I'm like, okay, I've got my 24 electrons. One's on the product side, one's on the reactant side. So when I add them together, my 24 electrons will cancel. Perfect. I notice that I have 32 hydroxyl groups on the reactant side and 24 hydroxyl groups on the product side, and so I know that I can cancel and subtract 24 from here to give me 8. I look at the number of waters. Okay, I have 12 waters on this side and no waters on this side. Okay, that's fine. 8 bromides. Again, everything else seems to be in order. So then I'm going to take all my reactants, write them down here, all my products, write them down here, and then double check my charge. I have -1 times 8, that's 8. This is 0 times 8, so that's 0. 12 times 0 is 0. 3 times -1 is -3. Perfect. I have -3 times -1, -3. I have 8 times -1, that's -8. Those all equal to -11. Perfect. We've done this correctly. All right. Pause the video, go outside, do something, come back. I mean it. Don't skip through it and be like, oh, I'm going to keep going. I'm serious. Take 10 seconds and go somewhere else. Look away. A quick summary of redox that I want to go through after our mental health break is knowing the process of oxidation and reduction always occur together. If you are reducing something, something has to be something has to be influencing that gain of electrons or the loss of electrons, right? So if something's being reduced, that means that it is becoming more positive, and therefore something else is becoming more negative, and vice versa. So you need to be able to know that if you found something that oxidized, unless it's a half reaction, which is why we call them half reactions, the full reaction is going to be the other half of that. So it's either the oxidation half or the reduction half. As well, oxidizing reagents are good electron acceptors. Those are the things that are going to be reduced. So oxidizing agents are electron acceptors that are being reduced. And that's why the reason why we call it an oxidizing agent is because while it gains electrons, something else is going to be oxidizing. Again, that process, they occur together. That's kind of what this is hinting at. With reducing agents, it reduces something, and therefore itself will be oxidized because it itself is going to reduce something, and therefore it will be oxidized. So it's really a good electron donor. It likes to give electrons away, and because it's giving electrons away, it's oxidizing, but something else is being reduced because something else has to gain those electrons. Again, they are always together. This is why those agents are there. This is Nernst. He's the guy who's the reason we have Nernst equation. I know you're like, Victoria, gross. German physicist who created this wonderful thing about electricity that I hate. I know. But he's actually very wonderful and brought us how to balance not only relating cells to redox, but also relating that to equilibrium constants and then making it work with solution, making us understand why adding salt to water makes it more conductive. All right. So how do we count those numbers of, oh, not what I wanted to do. Everyone's been asking me basically counting the number of electrons for Nernst, so I put 2 equations here. And basically, it's just the number of moles of electrons that you're doing. I also wanted to put the cathode in case anyone wanted to actually solve these. But it's just the number of electrons. So here I see that there's 2 electrons being transferred in either one of these. And I do have an example of when that's not the case. But most of the time what you'll find is it's the number of electrons that are being transferred in the equation. And usually they are the same. And so that means that we basically just use n equals 2 here and then like n equals 3 here. Okay, calculating the electron potential for the reaction. I've given you the electron potential equation here. All right, so basically what you're going to do is you will have your cell and you're going to write out the full equation, and this occurs at 25 degrees Celsius. So again, standard, that's what we wanted to know. And then it also gives us L of Q. I'm going to plug in my standards in here to get my E standard cell, and then I just plug it into the reaction, or plug it into the equation. Simple and steady. Isn't it RT over NF? Isn't it? Pretty sure. Yeah, I've done a typo. Your reaction quotient, again, is always going to be products over reactants. Gives me Ln. Take this, do the math. I get 1.59 V. And I'm doing double check that I do get 1.59 with the right equation, just for fun, because I, as we all know, am not a math wizard in the slightest. Multiply this and then divide by N of F, which is 3 times. Divided by 3 times 96485. Multiplied by the natural log of 0.0227. Yeah, well, division, as always. I knew there was a typo. I tried not using equation stuff, and then I think it got me into a pickle. Anyway, same idea here. You're literally just going to have 2 electrons transferred. We saw that before. And then you're going to use your E standard cell that we got from taking the cathode minus the anode, or if you're one of those people, the E reduction plus E oxidation, which is really E reduction minus the opposite charge of that oxidized reaction. Saying that out loud went funny. And then what you're going to do is you're simply going to take that standard cell, subtract the gas constant multiplied by the temperature divided by the number of moles that we found to be 2, because again, when we look at these half reactions, they're both 2 plus, and that means that they're both going to be transferring 2 electrons to balance themselves. Which means this is 2 here. And then taking that forward to here, and then taking your Q, again, products over reactants. This divided by this equals 67. Large number, which means if you have a large Q, probably is going to be great. This means that the equilibrium constant is going to be less than the reaction quotient, which means it would probably shift towards the reactants, in case we're wanting to allude to previous chapters. And then I'm going to quickly do the math on this one more time, just to make sure I've done that correctly as well, because this is now 2. Just to make sure I've written everything out for you correctly. This is why I love a TI-89. I don't have to retype everything. Yes, and this will be 2.2. Is that correct? Let's look. What was, I didn't put in 67. I was like, how did that happen? I didn't replace everything correctly, of course. 206. Oh, 206.6, so it is 2.7. Huh. I was sitting there for the longest time and I was like, what? I did do the math right. I just didn't change it when I was copying these over to here. Silly me. But anyway, it's 2.07. Okay. Calculating the cell potential in galvanic cells. So this is something that I wanted to try and especially show you with something that doesn't have the same, or what doesn't seem to be the same number of electrons transferred. But what you would do is, when you're trying to find the N part, because everything else is very similar, I know what I did. I copied these over from previous slides, and I still didn't put the division in. Back to what I was saying. So for finding the number of electrons in total, what you're going to do is, you note that, remember from way before when we were having to multiply the charge here by the top, but what I really meant to say was you multiply the 2 rows by the number of electrons to get them to cancel. So I multiply this top row by 2 and I multiply this bottom row by 1. here. And when you do that, you get this overall reaction here. Ooh, I didn't mean to write through it, but here, wait. And so when you do that, you note that the actual charge difference between these two then, to cancel these two out, would be 2 electrons, right? Because if I multiply this top row by 2 and I get these 2 FEs, that means that there's now 2 electrons in this top row. And in this bottom row, all of these are multiplied by 1 and therefore still 2 electrons. So that is why N equals 2 in this one. Just do that for all of them. But you always want to make sure that you're using the lowest common multiple. You don't want to just willy-nilly transfer them. So make sure that, if this is 2 and this is 4, then overall it's going to be 4, right? It's not going to be 8. Like, you won't multiply this bottom row by 2 and this row, you just multiply the bottom row by 2. All right, now we do cathode minus anode, or you can do reduction plus oxidation. Either way, you'll get the same answer. I got these from the table. And then I plug this in, again, making sure I wrote this correctly here. I plug everything in. This is what I get for my Q. Again, remembering that your coefficients now count, because remember, I had to multiply this top row by 2. This is another part that people miss. So please note that your Q now has 2's in it, because you had to get these electrons to cancel, and therefore to find your N value, which also means that N value is 2 only because you have this reaction scheme, and therefore that your Q is going to have to be to this reaction scheme, which is why we've raised these to the power of 2. And then you're going to get 0.0110, and now I just plug things in. I plug in my E standard cell, which I got. I plug in my R, which we know and given. I plug in my temperature. I plug in Faraday's constant. I plug in my 2. And also my reaction quotient, and I get 0.678. Makes perfect sense to me. Okay, now this one is showing how to calculate the equilibrium constant when you're given the Ecell values. This is the final one that we're going to go through today. And basically, I did put this one in right. I'm so proud of me. It's just as you saw before. When you're getting E equals Ecell minus this, and that's just to say that Ecell actually equals these values. So first thing I'm going to find is Ecell, because remember, I'm not looking for Ecell now, I'm looking for K here. And so I'm going to take the cathode, subtract the anode. Again, you can do reduction plus the oxidation. Just remember to take the opposite sign of the oxidation. You're going to take these values, which I wrote here just because I wanted you to see that I got them from the table, and you don't have to go look at that table. And I plug them in. Again, subtract, but this is subtract, so they actually get added together. I didn't flip the sign was already negative, and I get 0.8298 volts. Again, then I just rearrange this to be Ecell multiplied by NF over RT, so I just took this over here, but I had to divide it by these values, and therefore that just flips them. And then I just plug things in. So I plugged in I plugged in my Ecell, I plugged in my N equals 3. Again, we know, N equals 2. Did another math here. N equals 2, multiplied by 96485, divided by the gas constant and divided by temperature. And then if we do all of that, pull up my handy dandy TI, you get 0.8298 multiplied by 2, multiplied by 96485, enter that, divide by 8.3145, multiplied by 298. Ooh, I need to put in parentheses, I'm sure. That's the only thing about this that goes silly. Ooh, yeah, and I get 64.63. And then I just take e to that, because remember, to get the natural log out, I have to then take the e to both sides in order to get that value. So I'm just going to raise this to e, or raise e to this, and then I get into the answer, which will be 1.1, or 1.2, sorry, because I can only have 2 sig figs, of 10 to the 28th. Awesome. Okay. Apologies for all the tiny math errors. It's because I was copying things through, and I want to get this video done early. Okay, so that is all for your exam reviews. I hope these were really, really helpful. I am really looking forward to your questions and the office hours, and I cannot wait to see you then. Good luck studying. Email me anything you need, and I will be there. Okay, bye guys.